Hello, welcome to today's lecture on writing and balancing chemical equations. The first thing I want to get out of the way is a quick disclaimer that when you're writing or balancing equations, there's no one right or wrong way to go about trying to get these things to balance. There's just a lot of trial and error involved, and the more you do it, the better you'll get at it, but it just takes time to learn the process. However, we use chemical equations to represent changes in matter. When one thing is reacting, it turns into something else. That's basically what we're talking about when we say chemical change. So in this lecture, you're going to find out that equations are like recipes for chemical reactions. You'll also learn how to write equations, and you will have to also remember how to write the correct formulas for compounds. So let's get started, shall we? The goals of this presentation are to help you to understand the law of conservation of mass, to learn how to write chemical equations, and to learn how to balance chemical equations. First of all, when writing a chemical equation and making it balanced, we have to obey the law of conservation of mass. The law of conservation of mass simply states that you cannot create something out of nothing. Matter can neither be created nor destroyed. You cannot create something out of nothing. Likewise, you cannot destroy something completely and disintegrate it into nothingness. So there you go, the law of conservation of mass. Life is all about balance, and therefore we have to obey the law of balance when we're talking about chemical equations and chemical reactions as well. So as I was saying, the purpose of a chemical equation is to really give a set of instructions for chemists to follow. It's like the recipe, like we just said a few moments ago. Equations can also be used to make predictions about whether a reaction will even occur, and if a reaction does occur, we might even be able to predict what the products of the reaction would be. Let's get a few terminologies out of the way real quickly before we get too much farther into this. First of all, we want to know what a chemical reaction is in the first place. As I stated a couple moments ago, it's a process where one or more substances change into one or more different substances. Basically, you start with something, you end up with something different. That's how a chemical reaction works, and that's what a chemical change really is. The next one is the reactants. The reactants are the things you start with. They're the substances that you begin and mix together or start with in a chemical change. The reactants are always listed on the left side of an equation. Next are the products. The products, those are the substances that are formed from the chemical reaction. When you put some things together, you get something different formed, and that's what we call a product. Products are always written on the right side of the reaction arrow. The last thing I want to remind you of is the diatomic elements. Remember, there's those 7 elements: hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, and fluorine. Whenever these elements are found in a reaction or in an equation without being combined into a compound with something else, they will always occur in 2's. And so the formula for hydrogen gas would be H2. So now let's talk about the overall process for balancing equations. There are several steps to this. The first one is when you're setting out to write a balanced equation, you must first determine what are the starting substances and what are the ending substances. What are the reactants and what are the products to begin with. Once you've determined that, you want to write a word equation. The word equation is simply the names of all the substances that take place and the order in which they combine and are produced. After you write the word equation, you translate that into a skeleton equation. The skeleton equation shows all of the formulas in the order that they are mixed together and produced. From the skeleton equation, that's when we begin to make our balancing. To balance an equation, you must have exactly the same number and type of each element on both sides of the reaction, the reactant side and the product side. When you write the skeleton equation, you must, as I said before, make sure that you get the formulas written out exactly correctly. You have to make sure if it's an ionic formula that the charges of the ions add up to 0. If you don't start with the correct formulas, you'll be messed up throughout the whole process. So once you have the formulas written down correctly, then you begin to change the numbers of those formulas that you have on each side of the equation to get the same or the right number of each element on both sides. So that's where we use what we call coefficients. A coefficient is a number that's written in front of a formula, and that is used to balance the equation. Remember, we can never change the subscript on a formula. For example, water will always be H2O. If we need more oxygens on one side or the other, we cannot change the formula of water to H2O3 just to make sure that it balances. Water is always H2O, so the only thing we can change is the number of times we use that formula in our equation to get it to balance. So here we go. Let's write us a word equation, shall we? To write out a word equation, what you do is you write the name of your first reactant. Seems pretty simple. So write the name of your first reactant, and then you place an addition sign or a plus sign. After that plus sign, you write the name of the second reactant, if there is one. Then you write a yield sign. A yield sign is nothing more than an arrow pointing to the right or pointing toward the product side of the equation. After that arrow, you write the name or names of the products. If there's more than one product, you separate them by an addition sign as well, or a plus sign. So that is how you write a word equation. So here's an example of one. We have hydrogen plus oxygen yields water. Now the reaction arrow here, or what we call the yield sign, that can actually be used with several different terms. We can call it the yields, or we can say hydrogen plus oxygen react to form water, or we could say react to produce water, or we could say hydrogen and oxygen produce water. So any way that you want to say it to get the point across that water is what is being produced from the hydrogen and the oxygen reacting. So there is a word equation. Now, once we've determined our reactants and our products, we've written a word equation, then we need to translate that word equation into a skeleton equation. And simply, when you write a skeleton equation, you're replacing the words of the formulas with the names of the compounds that those formulas represent. Again, make sure you balance the charges and write the correct formulas. So here, our word equation, hydrogen plus oxygen yield water. Well, we have hydrogen, H2, plus O2 for oxygen yield H2O for water. So there's a skeleton equation. Notice that that is not a balanced equation, because even though we have two hydrogens on the left side and two hydrogens on the right side, we see that there are two oxygens on the left side, but only one oxygen on the right side. So this is our skeleton equation, not our balanced equation. So now that we've written our skeleton equation, we want to start using coefficients to balance the equation. Again, remember, you cannot change the formulas. You can never change the subscripts on any of the formulas. You can only change the number of times you use that formula in the reaction equation. And changing the number of times, that means writing a coefficient in front of the formula that you're talking about. So let's use some coefficients to balance an equation. I have here a skeleton equation for lithium reacting with calcium nitrate to produce lithium nitrate and calcium. The best way to start out by balancing the equation is to make yourself a nice list, an inventory with you, if you will. It's like a bookkeeping thing here. What you see on the left side, you see a lithium, so you write lithium. You see a calcium, so you write calcium. And you see nitrate ion, so you write nitrate ion. Now, one of the little tricks here that you can remember is if you have polyatomic ions like nitrate, you want to try to keep those together as much as possible. So if you see on the left side you see nitrate ion, and on the right side you see nitrate ion, and there are no other nitrogens or oxygens in any of the other formulas of compounds there, then you can pretty much stick with keeping that nitrate ion together. So we'll count the nitrate ions as one thing rather than counting up the nitrogen atoms and the oxygen atoms separately. On the right side, you want to make your list, again, your inventory list of what you have on the product side of the reaction. Lithium, you have a lithium. Calcium atom, you have a calcium atom. And a nitrate ion, you have a nitrate ion. When you make your list, you need to compare the left side with the right side. If they don't match up, you're probably looking at something wrong. So check to make sure you have the same list on both sides of the reaction arrow. So then we count how many of each type we have. And as we said, 1 lithium, 1 calcium, and 2 nitrates on the left-hand side. On the right side, 1 lithium, 1 calcium, but only 1 nitrate on the right-hand side. So in order to balance the nitrates, we need to put a coefficient in front of lithium nitrate. As we said before, you cannot change the formula for lithium nitrate. It has to be LiNO3. Therefore, we can put a coefficient of 2 in front of the lithium nitrate formula. Then that changes our lithium count on the right side. Now we have 2 lithiums, but we do have 2 nitrates, which balances the 2 nitrates on the left-hand side. Now we have to go back and balance our lithiums. In order to balance the lithium, we simply put a coefficient of 2 in front of the lithium on the left-hand side. So here, as you can see, we have 2 lithiums on the left-hand side, 1 calcium on the left-hand side, and 2 nitrates on the left-hand side. And we have exactly the same thing on the right-hand side. 2 lithiums, 2 nitrates, and 1 calcium. And voila, the equation is balanced. Don't forget to write your inventory lists on both sides of the reaction arrow and count up the number of each type of atom or ion that you have. So as we're about to wrap up here, let me remind you of a few key things to remember as you go out to start balancing chemical equations. First of all, you have to have the correct formulas before you can balance anything. If you don't have the formulas correct, you will be off from the get-go. I cannot stress this enough. I don't know how to emphasize it enough, but you have to have the correct formulas. So make sure you have your formulas correctly written with the right number of and type of each atom in the formula. Make sure the charges are balanced in the ionic formulas, and make sure you have the right number of atoms in the molecular formulas. So you have to have that before you can go on. Then always make sure you make a list on each side, your inventory list, and add up how many elements of each type you have on each side and compare. And that's where you'll be starting from after you get the correct formulas. Then also remember to try and keep your polyatomic ions together as much as possible. That should do it. I wish you the best of luck as you continue to learn chemistry and move on with balancing and writing chemical equations. Hi, welcome to Practice Balancing Equations. Today we're going to take a look at 3 different reactions. Then after each one, I will explain and walk you through how to balance the chemical equation. First off, you can see we put some concentrated hydrogen peroxide in a beaker, then adding some water just to dilute it down a little bit. Then to get that reaction going, we're going to add a catalyst called manganese dioxide. It doesn't actually participate in the reaction, it just speeds up the process for hydrogen peroxide to decompose to form water and oxygen gas. In that close-up, you can really see that reaction going strong. Here I have the word equation and the skeleton equation for the reaction you just saw in the video clip. Hydrogen peroxide decomposes to produce water and oxygen gas, or H2O2 yields H2O plus O2. Now we can use models to represent these molecules, and if we do that, we can use little colored discs to represent the hydrogen molecules as well as the oxygen molecules, or atoms rather. And if we do that, we can build a hydrogen peroxide molecule by putting 2 hydrogens and 2 oxygens together like so. That would be our original reactant. Now on the product side, we need to build a water molecule which has 1 oxygen atom and 2 hydrogen atoms in it, and so that would look a lot like this right here. So if we get that built, then we can build our other product, which is oxygen, which, if you recall, oxygen is one of those 7 diatomic elements, and so it's going to have 2 oxygen atoms bonded together because it will always occur that way. Now notice that we have 2 hydrogens on the left side and 2 oxygens on the left side. On the right side we have 2 hydrogens, but on the right side we have 3 oxygens. And that is not balanced. We have to have the same number of each type of atom on both sides of the reaction. So therefore, we have to start adding different molecules. We're stuck with these 3 oxygens over here because the formula for water is H2O and the formula for oxygen is O2. Therefore, we would have to add another hydrogen peroxide molecule to this side, to where we have now 4 hydrogens and 4 oxygens on the left side. And in order to satisfy the balance requirement, we would want to put another water molecule over here. And now, if you count up the number of reds and number of blues, or the number of hydrogens and number of oxygen, you will see that the equation is balanced. Therefore, that leads us to putting a coefficient of 2 in front of the formula for hydrogen peroxide, a coefficient of 2 in front of the formula for water. You can see we have 2 of each of those on both sides of the arrow. But our oxygen molecule is still only 1. So we will not normally write a coefficient of 1 in front, which is why I use that hollow 1 there to represent that coefficient. It is a 1, but in normal cases we would not write the coefficient next to the oxygen because it is only 1. In this reaction, you see a clear solution of lead-2 nitrate in the test tube. As the reaction proceeds, what we're doing is we're putting drops one at a time of a potassium iodide solution into the lead-2 nitrate. And as you see that solid yellow cloud forming, you'll see that that is the actual reaction between lead-2 ions and iodide ions, forming lead-2 iodide. That is not soluble in this solution. We call that a precipitate. Here's the word equation and the skeleton equation for the reaction you just saw. Lead-2 nitrate reacts with potassium iodide to produce lead-2 iodide and potassium nitrate, or PbNO3 taken twice plus Ki yields PbI2 plus KNO3. The yellow solid that you saw clouding up that liquid was lead iodide, lead-2 iodide, and that is what we're going to be showing in our models here with our colored atoms. So here's the lead atom. We're going to put with that the nitrates, the 2 nitrate ions that are associated with the lead. Here's the 1 ion, and here comes the 2nd ion. So lead-2 nitrate is reacting with potassium iodide. So potassium has a potassium atom with an iodine atom. There we go. And there we go. There are 2 reactants. And now the products would be lead iodide, lead-2 iodide. And so here's a lead atom, and it's going to have 2 iodine atoms with it to make our PbI2. And then the other product is potassium nitrate, so we'll need a potassium atom with a nitrate ion. And there is our, well, almost, there's the nitrate ion. So now we have our 2 reactants that are forming our 2 products, and you can see very quickly that there's only 1 nitrate on the right hand side, but there are 2 nitrates on the left hand side. There's likewise 1 iodine on the left hand side, but 2 iodines on the right hand side. So we need to figure a way to get this to balance. If we ended up with 2 iodines, then we must have started with 2 iodines. So therefore, what we would need to do is bring out another potassium iodide molecule to react to form the 2 iodines with this lead on the right side. We still need to balance the nitrates as well, because there are 2 on the left but only 1 on the right. So in order to do that, we also now have 2 potassiums on the left. We need to end up with 2 potassiums on the right. So there we have another potassium nitrate ion or another potassium nitrate molecule to come out there and make it balanced. So we now have one lead, two nitrates, two potassiums, two iodines, and two iodines. And our equation is now balanced. And you can see that we need to put in our coefficients for the one lead 2 nitrate, which again we don't put in a coefficient normally, but I put that hollow 1 just to show that there is a coefficient of 1 for it. But there are two potassium iodides, two Ki's, so we put a coefficient of 2 in front of that. And on the right hand side we have just the one PbI2, and we have two KNO3s, two potassium nitrates, so we got to put that coefficient of 2 right there. Now here you see baking soda is being put into a bottle. We're going to add some vinegar. All of you are probably familiar with this reaction, so it forms a lot of bubbles. We're going to stretch a balloon over the top of that bottle to catch the carbon dioxide gas that you see being formed from the reaction of sodium bicarbonate and acetic acid, or baking soda and vinegar. So sodium bicarbonate reacts with acetic acid to produce sodium acetate plus water plus carbon dioxide. NaHCO3 plus HC2H3O2 yields NaC2H3O2 plus H2O plus CO2. Oof, that was a mouthful. But here we go with our models. Let's make a sodium bicarbonate first. We'll bring out a sodium atom. And then remember, we're going to try to keep our ions together as much as possible. So let's bring out a bicarbonate ion, an HCO3. And then to make our acetic acid, we have to have the proton or the hydrogen atom to start with. And then we'll bring out our acetate ion, which is the C2H3O2. And we'll put that on with the hydrogen there. So now we have acetic acid and sodium bicarbonate. And those are going to produce our sodium acetate, which means we need to have a sodium atom. Oops, like I think we'll bring the acetate ion first. And then here comes the sodium atom. So we have sodium acetate. And then we'll have water, will be another product. And the third product would be carbon dioxide gas. So here it is right there. Now what you can notice here is when we're trying to balance these things, we want to make sure we have the same number of each type of atom on both sides of the arrow. And you'll see we have a sodium on each side. We have 1, 2, 3 carbons, 1, 2, 3 carbons, 1, 2, 3, 4, 5 oxygens, 1, 2, 3, 4, 5 oxygens, and our hydrogens are also balanced on both sides of the equation. So there we have the reaction. The skeleton equation actually turned out to be balanced as it was written because we have one of each of the molecules that were reacting and produced from this equation. Well, alright then, thanks for watching, and get out there and have some fun balancing chemical equations.